Log on, tune in, find out. Another good idea from Cambridge.
Speaker rather than the other author at the same time. It's a special pleasure to have Andrew Brooke-Taylor. Bousfield lattice from a set-theoretic perspective.
Thank you, Philip. So I believe I'm supposed to start by saying how long I'm here. Only a week, and that ends Thursday morning. So if you want to talk to me about this, better get in quick. But Benedikt Löwe and Birgit Richter, who I'm working on with this, will be around for much longer. So maybe talk to them. Okay, so this is stuff about homotopy theory from a logician's point of view. So, I mean, Peter gave us a very nice talk about doing logic using homotopy. So if they both go well, maybe we can understand logic using logic by putting them together. But really, this was a case of there's this thing in homotopy theory that's very poorly understood, and it's got some set-theoretic structure, and we're hoping to get at that using a set-theoretic perspective. So let me give some definitions. So if you've got a couple of base-pointed topological spaces, x and y, then two very standard constructions in algebraic topology are the wedge sum, which is basically the disjoint union, but then you identify the two base points to be the new base point, and also the smash product, which is basically the Cartesian product, but modded out by identifying all of the image of the wedge, essentially, down to a base point. So these are fairly fundamental constructions. Note that smash distributes over wedge. In fact, smash distributes over arbitrary wedges. If you just think it through in terms of the Cartesian product and the union, it all works out just fine. So variance on these two operations are the key operations for what we're working on. So we want to look at stable homotopy theory, and for that we're not so much interested in topological spaces as spectra. So a spectrum consists of a sequence of topological spaces, and between any two of them we have these structure maps from the suspension of each to the next. So the suspension is what you get by smashing the circle with something. But intuitively you just think of them as being like spaces. And also we're only really interested in them up to homotopy theory. Now, as I was saying, the wedge and the smash, they also extend to spectra. I said dimension-wise, I guess it should have been component-wise, but you basically do the natural thing on each xi, and it all washes out. Okay, so some spectra that we'll use are the one-pointed space for every xi, and since we're only interested up to homotopy equivalence, actually any contractible space. That is an important one. The other really important one is the sphere spectrum. So in negative components you just take the one-point space, but then in positive components you take the n-dimensional sphere. And then note that if you've got two spheres and you smash them together, then just the dimension adds up. And so in particular the structure map we can just take to be the identity map or the canonical homeomorphism, however you want to think of it. Now we're going to be doing some set-theoretic talking about power set of the naturals, so we need some other examples, and so I don't expect you to know what this is. I myself don't really know what this is, but for any fixed prime p and any natural number or infinity, we have the nth Morava K-theory spectrum. So the point about this is, well, the reason that we're interested in spectra really, well, one of the nice things about spectra is that you've got these generalized homology theories and generalized cohomology theories that algebraic topologists are interested in, and they correspond in a very close way to spectra. You can get each from the other. And so this is a kind of spectrum that corresponds to the generalized homology theory known as the nth Morava K theory. So that's an important example for what we do. Okay, but if you want, you can just forget all that background and just think of this purely abstractly. What we're thinking about is we want the Bousfield class of a spectrum. We're going to say that that is the collection, the class of all spectra that smash with E to give 0. And so those spectra are sometimes called acyclic. We order these Bousfield classes. So for each spectrum E, we've got a class of spectra Z. We order it by reverse inclusion. So the Bousfield class of X is less than the Bousfield class of Y if and only if it's greater as just a class in the usual set-theoretic sense. Or to put it another way, if X is less than Y as Bousfield classes, if and only if for every spectrum Z, Z smashes with Y to 0, if and implies that Z smashes with X to 0. Okay, and so B will be our notation for this collection of all Bousfield classes, partially ordered in this way. Now, if you worry about that sort of thing, you might start to be concerned that, you know, these Bousfield classes are proper classes, and now I want a collection of those. And okay, we could just take representative spectra E for the Bousfield class of E, but still we'd probably have boldface B there, the Bousfield collection, being a proper class, at least naively. But okay, I'll get back to that. What can we say a bit about that partial order first? Well, this contractible, the 0 spectrum is a minimum in this partial order because anything smashed with 0 is 0. Anything smashed with a single point is a single point. At the other end, we've got the sphere spectrum is a maximum because anything smashed with the sphere spectrum is itself. So in particular, the only thing that smashes with the sphere spectrum to give 0 is 0. Okay, so we've got a top and a bottom. Now, since the smash product distributes over joins, if you take, well, distributes over wedges, if you take this wedge of a collection of spectra, then that actually gives you the least upper bound of the Bousfield classes in this partial order. So that fits in beautifully with sort of standard notation for partial orders. Sadly though, smash does not give us the greatest lower bound. And so a lot of the intricacy of what goes on in this setting is to do with the fact that smash is not the greatest lower bound and different variants on that problem. On the other hand, smash does respect this less than relation just by appropriate, clever bracketing of the smashing. So we've got that this class B is an upper semilattice. We've got arbitrary joins and so the big question is, do greatest lower bounds exist? So to solve that problem, actually we've got this lovely theorem by Okawa from the late 80s saying that actually there are only set many Bousfield classes. In fact, there's somewhere between continuum and 2 to the continuum of them. And so as an immediate corollary of that, we can say that the greatest lower bounds of arbitrary sets exist in this partial order, just because you know that there's at least one lower bound, namely 0, so you just take the join of all the lower bounds. Now we couldn't do that when we thought B was a proper class, but now we know B is actually just a set. We can do set size joins. So we do have greatest lower bounds. It's just that they're not the smash. Okay, so the really big open question in this area is what is actually the cardinality of this Bousfield? Well, we've just shown that it's a complete lattice. What is the cardinality of this complete lattice? Could it consistently lie strictly between 2 to the aleph naught and 2 to the 2 to the aleph naught? Of course, as a set theorist, that's a natural question. We don't really have any reason to believe that it could be strictly in between, except that we also don't have any idea how to tie it down to one of the endpoints at the moment. So you never know, one can hope. But that seems to be a big problem, and we need to warm up to that. So we're going to now delve down a bit more into the structure of B. So, I mean, this issue that the smash is not the greatest lower bound is a bit annoying. So what we'll do is move to a sub-lattice of B. So we'll define DL to be the set of those Bousfield classes which smash with themselves to give themselves. Okay, this is something that you have to have for a greatest lower bound. It's straightforward, purely algebraic manipulation to show that DL is closed under smash and join. Also, if you've got something in DL and it's less than 2 spectra x and y, then that line there shows that actually it's less than the smash, and so it must be that smash is the greatest lower bound in DL. So now so DL is what we were looking for. It's a situation where smash is the greatest lower bound, and moreover, because smash distributes over join, it's a distributive lattice. In fact, smash distributes over arbitrary joins, so depending on your favorite terminology, DL is any number of things. Okay, but as a set theorist, I mean, a distributive lattice is nice, but what I'd really like is a Boolean algebra. So can we get that? Well, for a Boolean algebra, you want a complementation operator. So let's let little a, that will be our complementation operator. Well, let's just take it to be the join of everything that smashes with x to give 0. Okay? So actually, Bousfield, back in his original work, gave an equivalent definition, but his work predates Okawa's, so he had to explicitly construct something rather than just lattice theoretically saying take the join. But we can do this, and then we define BA to be the set of those x such that x join AX is this maximum element S. It turns out by basic algebraic working that x smash AX will always be 0, but it need not always be it need not be the case that x join AX is this maximum, the sphere spectrum. So it's straightforward to see that BA is a sublattice of DL. On the other hand, BA does not have arbitrary joins, and these funny spectra that I introduced earlier on, the Morava K-theory spectra, gives an example of that because the KNs are in BA, but the join of all the KNs is not in BA. So just an algebraic topology fact that we'll appeal to. So, okay, we've got a Boolean algebra. What about a complete Boolean algebra? I mean, we've got arbitrary joins floating around. That would, maybe we can get a complete Boolean algebra. Well, if we want that, we should probably add some more, I've said add more sets there. I really should have said add more spectra. BA has joins, but not arbitrary joins. We want to add more spectra in. So for the purposes of adding in more spectra, the idea that the complement A of x could land outside our distributive lattice is going to be a problem. So what we do is we look at a retraction from the whole Bousfield lattice down to this distributive lattice dl. So definition, the retract of x will just be the join of all the things in dl that are less than x. Okay? And that gives us the retraction from b to dl, and then we can redefine the complement to be capital A of x now is the retract of A of x. So of course on BA this is just the same complement, but on other things it might be different. Okay, so now with that complement defined, we define CBA to be those spectra such that the complement squared gives the spectrum back again. And then it follows from simple algebra and what I've already said that BA is a sublattice of CBA, is a sublattice of DL, is a sublattice of B. And CBA is a Boolean algebra. It in fact is a complete Boolean algebra. But whilst arbitrary meets as computed in CBA are the same as those as computed in B, this is not the case for arbitrary joins. So now meets work but joins don't. So let's give this a name, sort of curly wedge, curly V, is going to be the join in CBA. Okay, so we've got this subset inclusion. Now another spectrum known as the Brown Combinates dual of the p-local sphere spectrum is in B but is not in the distributive lattice DL. So we know that DL is a proper subset of B. So a lot of, well, I think everything I've said so far can be found in the paper. There's a key paper by Hovey and Palmieri talking about the structure of the Bousfield lattice. And they give an argument that CBA must be a proper subset of DL, but they don't do it constructively. So that's the first question. Can we constructively get an element that's in DL but not in CBA? Now, they also argue that BA is a proper subset of CBA because BA is not complete because BA is not closed under joins in B, as we saw with the KNs. But that final logical step, you've got to distinguish between potential joins in BA and potential joins in B. So that's a bit unclear. We're still trying to understand what they meant by that. It's a subtle point. Maybe they even tripped up. Or maybe they had already thought of but didn't write down what I'm about to say next. Anyway, this is basically the point where we can start to contribute. So here's what we've been able to show. So if you've got a subset of this smallest sublattice, the Boolean algebra BA, then in fact the join of elements, the join of the elements of X is the same whether you compute it in CBA or whether you compute it in B. So let me draw a picture. We've got our Bousfield lattice. We've got DL. We've got CBA. And we've got BA. So here's S. Here's 0. We've got some collection of things in BA. We want to take the join as computed in CBA. The proposition says that in fact the join as computed in B will be the same thing. Okay? Even though for CBA in general they will be different. So, in particular, this implies that the wedge of the KNs is something that's in CBA, but as we've already seen, it's not in BA. So that already gives us a concrete example of something in that complement. All right, I think I do have time, so I'll quickly go through the proof. It's basic, it looks purely formal, but there's a couple of subtleties. So the definition, it turns out that the join in CBA can actually be given by a squared of the join in B. And so if you expand that out, well, A was just the retraction after the usual, the original complement. So we have that twice. Now, we can bring A through the join on that second line going down to the third line. And now because A of x for every x, well, each of the x is assumed to be in BA. So AX is also in BA. So in that context, we actually know that the meet is the same as the infinite smash. So we can do that substitution. Then with the infinite smash, the reduction doesn't do anything, so we can get rid of that for the next line. Then we can bring A through the infinite smash again to get R of wedge of these A squareds of x's. Now, although A didn't work as a complement operator, for whatever reason, it actually does still work that A squared is always the identity. So we can then cancel off the A squared. The reduction again disappears because we can see that we're in DL, and we get that indeed this is the wedge of x as computed in B. So it's not entirely formal because we've got different kinds of meets and joins floating around, but everything works out nicely from the assumption that our class was that our collection was a subset of BA. Okay, and so so we use that to show that actually there's something in the complement of BA in CBA. We're going to use it again. So now let's come to the question of, is there something, can we get a concrete element of DL that's not in CBA? Well, no, we're not quite able to do that, but we can give you two options such that we know that one of them must fit the bill. And we can do that in uncountably infinitely many ways. So the lemma that gets us there is the following. If we've got two spectra in DL whose smash is 0, but such that the meet as calculated in B is not 0. So there's some element, possibly just in B, that's less than both of them. Then one or the other or the join of them must be in the complement of CBA. And again, that's a similar flavor of proof. It looks like it's almost formal, but there is the issue of where different meets and joins are happening to worry about. So from that lemma, we've got this corollary. For every prime P, and for every subset S of the natural numbers, then at least one of either K infinity or the infinite wedge of the Kn's, where N ranges over S plus you've put infinity in. So one of those two, possibly both, lies outside of CBA. So because this is true for every prime P and for every subset of the naturals, that means that for a start, this complement, DL without CBA, that is infinite. And moreover, if it's not the case that it contains every K infinity, as P varies, then in that case, it must be that one of these infinite, well, if k infinity for some particular p is not in there, then for every subset of the naturals, we've got the other one not in there. And we know actually that those are all different. So then it tells us that we've got the cardinality of the complement is in fact at least 2 to the aleph naught. And so the proof is just using this lemma. We take x to be k infinity, y to be the join of all the kn's, and e to be this funny other spectrum I mentioned before, the Brown-Combinator's dual of the p local sphere spectrum. It turns out that e is less than both x and y, as I've defined it there, but it also turns out that the smash of x and y is 0. So from our lemma, it turns out that, well, the conclusion of the corollary helps. So I think I'll leave it there.
Questions, comments?
Yep.
Forget the definition, but is B a quantile?
Were you saying you forget the definition of a quantile?
Yeah.
I don't know. I also do not know the definition of a quantile.
The wedge is a kind of product, which distributes over the soup.
Right. I guess the wedge is a kind of co-product.
I mean the wedge,
the smash. The smash is very much a kind of topological version of a product. Yes.
I suspect it must be a quantile.
It's entirely possible. Yeah.
So I just wondered to what extent your constructions, the constructions you were talking about, can be applied in a more general context of quantiles.
I mean, it's possible that they do, because, I mean, a lot of what we've done here is just filter out the extraneous information, try to get down to the pure lattice theory of it, if you will, and then see what we can do from that as we're sort of building up. And so actually, once we're able to pinpoint the example spectra we need, these KNs and this Brown-Combinator's dual, then from that point it's all just sort of logic and algebra of the lattice. So it's quite possible that if you've got the right examples, then you can do exactly the same thing in any quantile. That's certainly possible.
Any other comments? Questions? Oh, okay, thank you very much.